So, hi everybody. My name is Noizet. I'm from France, in case you couldn't say by my accent. All right, so today I'm going to talk to you about a work I did with my PhD advisor, Alan Schmitt, at Rennes, at the University of Rennes and Inria, which is a work on how to generate interpreters. So the idea is to generate interpreters from a language which is called Scale, which allows to describe semantics, operational semantics of programming languages. You can find the work on GitLab, so at this address. And so I'm going to also show you how we can configure this interpreter to handle non-determinism. Some works already exist in this field. So the basic way to generate interpreters, to create interpreters, is to write them in OCaml, Haskell, or in Coq, and extract them to OCaml or things like that. It usually works, but the main issue is that if you use a shallow embedding, you cannot handle directly the AST of the language that you describe. And the design choices are really hard to update. So, for example, going from a shallow to a deep embedding or the other way around. And if you use a deep embedding, well, it's really heavy to handle. So there are languages like LemHot or the K framework, among others, which allow to describe the semantics of a programming language in order to use it then to generate, for example, interpreters or Coq formalization and so on. This is interesting. Scale comes in this field, but it is way more minimalistic than these tools. And one main feature with Scale is that it allows for different semantics for the same description of a language. So, in less words, with a nice picture, if I want to describe the operational semantics of a programming language, I can just write the semantics in Scale. So this is the only thing that the user has to do. And then you can put it in the Necro ecosystem to generate all kinds of stuff. So, for example, an OCaml interpreter, an interpreter written in OCaml, a Coq formalization, a debugger, and so on. So today I'm going to talk mainly about only about the Necro ML, so about the generation of OCaml interpreters. So first, let me show you what a skeletal file looks like. So this is the semantics of while, which is of imp, which is a while language, which is pretty basic. So you have algebraic data types. For example, the type of expressions is either a constant, variable, sum of two expressions, the equality of two expressions, or the negation of an expression. So it's pretty usual, as in any ML-like language. What is really interesting is that you have also unspecified types. So I don't specify how identifiers are represented, for example, for variables. I will also not specify how integers are specified. You can use nice integers which don't overflow and are not 64 or 63 or 32 bits if you want. And you can also specify expressions. So they are called terms. For example, the evaluation of an expression. But you can also leave unspecified terms. For example, lead to val, which translates a literal into a value, or read, which reads into non-variants. And when you specify, you have the usual ML constructs like pattern matching. You can also use destructuring let with let int equals. So an interesting thing is that it's not something that will raise an error. So if you want to add something that is not an integer, you will evaluate the expression and you get, like, for example, a Boolean, then let int e1 equals blah, blah, blah will just not work. So it does not raise an error. It's just a partial specification. So it makes no sense. So when you have that, so we have unspecified stuff, as I said, and we want to generate an interpreter, you have some work. So first use Necro ML. So it generates this file. This is just the beginning of the file. So for unspecified types and terms, on the left, you have the SK file, just the unspecified part. So it generates module types, as you can see. So a module type for unspecified types, and a module type for unspecified values. It also generates all this code, so this is not meant to be read, but basically it's just the translation of what was in Scale into OCaml. You have like constructs like apply and m.ret and m.fail because it's embedded into a monad. I will talk more about that later. But basically the monad is here to handle non-determinism and partiality. And then if you want to generate an interpreter, you will need to specify a module for both module types for unspecified stuff. So this is a file that I wrote to generate an interpreter. So as you can see, it's really short. It does 31 lines. And you just have to, so you give a module type, a module of module type types for the types, and a module for the values. Again, it's pretty basic. So identifier is string and addition is addition. You just have to add a monadic return because there is a Kleisli translation. So all arrows are translated into arrow m.t. And then you just have to do this make interpreter, and it generates an interpreter. Here it's a functor because I added the monad in argument. We'll talk about that just after that. So first, let's see a pretty basic example. So it's a factorial code written in imp. I use the ID monad, which is basically just nothing monad, the identity monad, because there is no partiality, no non-determinism, so it doesn't really matter. And so I evaluate the statement using the interpreter generated eval statement, which is the same as the scale eval statement. I evaluate also with the factorial, if you don't trust me, and you get 3,628,800, which, as you know, is a factorial of 10. And if you don't know, it's written just under that, which is the computation of factorial with this function that I believe you can trust. All right, so now let us add some non-determinism. When you write semantics of the programming languages, often, like for example with lambda calculus, you have non-determinism not really in the results because there can be some normalization results or things like that, but you have non-determinism in the way to get to the result. So you say maybe you can take this branch or maybe you can take this branch. So this is why we need non-determinism when writing an operational semantics, to our opinion. And so we had to while just an ambiguous operator which takes one of these of the expressions non-deterministically, and an assert statement which asserts that an expression is true. So the evaluation is just augmented by that. So the evaluation of amb is just I take one with this amb function, which is branch or end. So branch is the non-deterministic scale construct. And eval statement is added with the assertion, which says eval expression returns true. So as we said, if it returns false, then we just cannot evaluate assert. So it just doesn't mean anything. So here is a test for this. So we just had a code which is A is 2 or 3 and B is A plus A. So in this code, B is non-deterministically 4 or 6. With the identity monad, so this is identity monad. So as I said, the return does nothing. It's just the identity. And the way it handles branchings is that it takes the first possibility. And if it succeeds, then it stops and it returns the result. But if it doesn't, then it goes to see the other branches. And so we just get 4 because obviously 2 plus 2 is 4. So the first branch succeeds. But now let us assume that we add an assert that B is different to 4, different than 4. Anyway, so 4 is not going to succeed. So, okay, that's all right. There is a non-deterministic choice, so it's going to return 6, right? Wrong. Because the identity monad, as I say, takes the first branch. So when you say A equals 2 or 3, 2 is a success. So it says, okay, it's 2. And then when you assert that B is different than 4, it's too late. So this is why you have other monads, and this is why you need to have other monads to specify how you want to handle non-determinism. So in this case, we have a continuation monad which does some backtracking. So it's pretty hard to read, but basically the type is just a type of continuation. So it's a continuation passing style with a continuation, a failure continuation, which remembers what to do if we fail. So when you evaluate the 2 or 3, it says, okay, it's 2, but I keep a backtracking point, and I say if later I find out that it's not 2, then okay, I'm going to try something else. And so it does 2 plus 2. Assert 4 is different than 4. Okay, so it wasn't true, and it backtracks and gets 3. And so the result with the continuation monad, as you can see, is 6, because basically that's a good result. If you added a third possibility 4, it will still return 6, but then you can relaunch the monad in order to find out the other possibilities later. If you want to find out more about Necro, the development is available on GitLab. So it's gitlab.inria.fr/skeletons. There are some other tools. There is NecroCoq, which, as I said, allows to generate coq formalization for skeletal semantics. There is also Necro Debug, which is a debugger generator, because we found out that when we write a semantics, we do some mistakes. Sometimes it happens, rarely, but it happens. And so we need a debugger to be able to track the issue. And there are lots of other, some other tools which you can find out about by going to this Git repository. Necro has already had some applications. So first, JScale is a project which consists on stating JavaScript semantics in scale, and that's why we developed Necro Debug actually. So it's an ongoing work, but already there are a lot of actual JavaScript programs that can be interpreted using Scale and Necro ML into a working interpreter. There is a work on, there has been some work, on automatic certified transformation from big step skeletal semantics to small step skeletal semantics, which will also be published at PPDP together with JScale. There is work on a certified interpreter generator. So this one uses coq instead of OCaml, and then is extracted to OCaml. So it's basically way slower, but it's certified, so you like what you like. And we have seen online that there are some people who are working on incrementing skeletal semantics with whole logics. So this is a part of work of Jorge Perez, and so this is Laura Andrea Shimbator Beicher thesis, sorry. All right. Now, if you have any questions on this development, you can go to skeletons.inria.fr, which gives a lot of pointers and a lot of papers on skeletal semantics. And of course, I can answer to any questions right now.